Hello and welcome back. In this lecture, as we discussed previously, we have a challenge station, some hard problems that it's very good for you to go through them, try to solve them. And in this lecture, I'm going into the details of solving them. So I have them in a separate file here because they probably take some space for solving them. Alright, so the first question is solve this equation 1 over x plus 1 over a plus 1 over b equals 1 over x plus a plus b, right? Now, the first thing you notice is that basically the equation is formed by summing all the denominators. Let me zoom in a little bit. By summing the denominators. So how do we solve this? What we can do, let's 1 plus a 1 plus b is equal to, let's bring 1 over x on the other side, x plus a plus b minus 1 over x, right? And then take a common denominator, a plus b, x, and then this goes to the first one, x comes up, this goes to second one, x plus a plus b comes up, and this becomes minus a plus b divided by x times x plus a plus b, right? And again, if we simplify this one, common denominator ap, a plus b, this is equal minus a plus b x times x plus a plus b, right? And then we can cancel out a plus b from both sides, x squared plus a plus b times x is equal minus ab. Therefore, x squared plus a plus b times x plus ab is equal to 0. And if you can see how it's very easy to realize how to factor this, x plus a x plus b is equal, right? X squared, xb, ax, and ab. And therefore the roots are minus a and minus b. And you kind of could guess that, right? You could guess that because in the original equation 1 over x, 1 over a, 1 over b equal 1 over x plus a plus b. Now it's very easy to guess that if I put x equals negative a, these two terms cancel out, I end up with 1 over b. Here they also cancel out, I end up with 1 over b. Similarly, if I put x equals negative b, I end up with 1 over a from the left side and 1 over a from the right side. And it's easy also to conclude that this should be a quadratic equation, and therefore we only have two roots, and x equals negative a and negative b is the root. Alright, the second question, if a, p, and q are real numbers and a is not 0, prove that the following equation has always real solutions. So again, if you simplify this and you end up with a quadratic equation, and a quadratic equation always has real solutions if delta or delta prime greater than or equal to 0. Okay, all right, so let's see how we do that. I think the easiest way to start with is to get a common denominator, x minus p, x minus q plus x minus p is equal 1 over a squared, right? And therefore we end up with a squared 2x minus p minus q is x minus p, x minus q. Okay, so a squared or 2a squared x minus p plus q times a squared. Okay, I'm just simplifying the left hand side. X squared minus p plus q x plus pq, the right hand side, and put everything, or bring everything to one side. Bring to one side. I bring everything to the right side. X squared minus p plus q plus 2a squared x plus pq plus p plus q is 0, right? So this is a quadratic equation. We expected that. And what's interesting here is the fact that what happens if, so the leading term is the coefficient of leading term is 1, the coefficient of x is minus this term, and the third coefficient is this. So delta is for the standard form is b squared minus ac, right? So p plus q plus 2a squared minus 4 times pq plus p plus q a squared. Now let's simplify this. So the first term is p plus q squared plus 4a squared plus 4a squared p plus q, right? 4pq minus 4p plus q a squared. And the reason I wrote this in this form, basically I assume the p plus q as one term is obvious here, because there is a 4a squared p plus q which cancels out with this term, and we end up with p plus q squared plus 4a squared minus 4pq, right? And if I simplify p plus q squared and minus 4pq, I end up with p minus q squared plus 4a squared. And since all of these are real numbers, and one of the properties of real numbers is that when you square them, they have to be strictly non-negative. So delta of this equation is strictly non-negative always. And therefore we always have real roots, no matter of what a, p, and q are. That's because the delta is strictly non-negative. Okay. The third question: prove that for every set of real numbers a, b, c, this equation has always at least one real solution. And again, at least one real solution. In terms of just by looking at this is a quadratic equation, and at least one real solution is that either delta or delta prime is positive strictly, therefore we end up with two real solutions, or delta or delta prime is 0, we end up with double roots, or two roots that are identical, so let's call it a double root. And it's real, right? Again, it's real. At least one real solution means delta or delta prime greater than or equal to 0. Alright, let's simplify it. X squared, so the first term is x squared minus a plus bx plus ab. So this is the first term. The second term is x squared minus b plus cx plus bc. And the third term is x squared minus a plus cx plus ac, right, equals 0. Therefore, we have 3x squared minus a plus b plus b plus c plus c plus a x plus ab plus bc plus ca. This should be. And again, so this is 2a plus b plus c. So because there's a factor of 2 here, it's easier to use delta prime, or that's my preference, so I'm going to write it down. This is my preference. when I see a 2 at the in the coefficient of x, I always use delta prime. So delta prime was b squared minus ac, right? So a plus b plus c squared minus 3 ab bc ca. And this if you square this term becomes a squared b squared c squared 2ab 2ac 2bc minus 3ab minus 3ac minus 3bc, right? And this becomes a squared plus b squared plus c squared minus AB AC plus BC. Okay, now the question is this always great? So how do we prove? We have to kind of prove this, right? If we have three real numbers a b c, a squared plus b squared plus c squared minus ab minus ac minus bc, is it really always greater than or equal to 0? Let's see. How do we prove this? In order to prove this, I'm going to make a very interesting tactic. So my tactic here is, or my plan, like this. Now this delta prime, I'm going to create it as a function of x squared minus b plus c x plus b squared plus c squared minus bc. Okay, now you see what happens here, right? I basically substitute a with x, right? Minus ab. So basically when I have a, I put x, because a could be any real number as b and c, right? And the point here is that if this quadratic equation is always positive, something like this, then I'm guaranteed that if I put x to a, if I put a back here, I'm also guaranteed to be positive, right? So again, another quadratic equation, I'm interested in the sign. Let's calculate the delta of this one. Let's call it delta 2, which is b plus c squared minus 4b squared plus c squared minus bc, right? And let's simplify this. So delta is 2 is b squared plus c squared plus 2bc minus 4b squared minus 4c squared plus 4bc, right? And this is basically minus 3b squared minus 3c squared plus 6bc. If I factor minus 3, then b squared plus c squared minus 2bc, right? And this is minus 3b minus 3 squared, and this is guaranteed to be less than or equal to 0, right? And if this is less than, if delta of a quadratic equation, this one, is less than or equal to 0, we are guaranteed that delta prime of x is the sign of function, the quadratic function is agrees with the sign of the leading term x squared, right? So this has to always be positive because delta prime, the leading term, is plus 1, right? Okay. And therefore, if delta prime of x is always greater than or equal to 0 for any x, then I can put x equal a. Delta prime of a is also this, and this is the delta prime of the original quadratic equation. Therefore it means it has at least one real root, right? So you see what we did here. We wanted to show that the original quadratic equation, the delta was positive or zero, and it was a quadratic terms for a, b, and c, right? And instead of showing that it's true for, it's always true, we assume that it has a variable x. Okay, and basically we removed a and we put x, and we said that okay, a could be any number, so let's define it as variable x. And then it became a quadratic equation itself, and we show that the delta for that quadratic equation is always 0 or less than 0, which means the quadratic equation should be always positive or 0. Okay, that's a neat trick, and that's a very interesting problem to solve. All right, the next one. If one root of equation ax squared plus bx plus c equals 0 is square of the other root. So if I have two roots x1 and x2, let's assume that x1 is x2 squared. This is the assumption, this is given. Then prove this relation. Again, we have 3 degrees of freedom, 3 degrees of, and then when we give a relation between the roots, we remove 1 degree of freedom, so we end up with 2 degrees of freedom, which means that if the two, there should be a relation between a, b, and c, such that if I plug in some numbers for 2 of them, the third one can be calculated from that equation. And we want to basically prove this, right? So how do we approach this? Again, what do we know about the roots, right? We know that the s, the sum of the root x1 plus x2, is minus b over a, and p, the product of the roots x1 and x2, is c over a. We already know this. And what I can do, I can in the product I can plug in the relation x1 is x2 squared, right? And therefore x2 cubed is a. Therefore I immediately find the value of one of the roots, c over a to the power of 1 over 3, and therefore the second root, or the first root, x1, is also given, right? I have to square this, c over a 2 over 3. And then now I have these two, I put them back in the sum, right? That's another relation. C over a to 2 over 3 plus, or maybe before do that, because I have a power of 1 over 3, let's cube it first. S cubed is minus b over a cubed, which is x1 cubed, x2 cubed, plus 3x1, x2, x1 plus x2, right? Which is okay, and therefore what we conclude here is that minus b cubed over a cubed is now you see in the problem we have c minus b and a minus b. The question is, where are these coming from? C minus b cubed, a minus b cubed, right? And let's see. So x1 cubed is c over a squared, plus x2 cubed is c over a, plus 3x1 x2 c over a, times x1 plus x2 minus b over a. So this is the relation. But then the question is, how do we make it in the format that the problem is asking? Let's see. So this is equal to c squared over a squared plus c over a minus 3bc over a squared. Let's make a common denominator a squared here. Alright, let's multiply by maybe a cubed minus b cubed is okay, let's see, c squared 3bc, and what I'm trying to see is how to make this in the format that the problem is asking. Now let's start with the problem is giving a c minus b cubed. Sometimes you don't need to start from scratch and get to what the problem is asking. You can simplify the problem and then start from somewhere to get to the simplified version. So a c minus b cubed is c a minus b cubed. If I'm given this, I can write down c over a to the 1 over 3, right? Is c minus b a minus b, right? So this goes this way, this goes this way, right? But c over a to the 1 over 3 is basically x2. This is what we found, right? So if I could write x2 in another way, then I have to prove that I can write x2 in the form of c minus b over a minus b. Right? So basically I have to prove this. If I prove this, I have solved the problem. Okay? Now how do we prove this? The way we're going to prove this is c minus b over a minus b. Alright, let's see. We start with substituting for x1, so x2 squared plus x2 is minus b over a, and x2, right? But let's okay, this is interesting. So based on the p, x1 times x2 equals c over a, we calculated x2 and then we calculated x1, right? But the thing is that x2 is actually a root, right? So and x1 is also a root. What does it mean? So if I put it there, and a x1 squared plus bx, or let's write it like this, a x2 squared, a x2 squared plus bx2 plus c should be 0, right? Because x2 is a root. So if I put it back in the quadratic equation, I should get 0. But x2 squared is the other root, x1, right? So ax1 plus bx2 plus c should be 0, right? So x1 is actually, now this is easy because I can see the relation between x1 and x2 in other form. So x1 is c minus c plus bx2 over a, right? But if I put it back into the sum, basically x1 plus x2 becomes minus c plus bx2 over a plus x2 should be minus b over a, right? And then let's multiply by a. So minus c minus bx2 plus ax2 is minus b, right? So bring c on the other side, so we end up with a minus b times x2 should be equal to c minus b. Therefore, x2 is c minus b over a minus b, and voila. Okay, so we proved that x2 is this, and we also proved that from the product that x2 is c over a to 1/3. So these two should be equal. So if we raise them to the power 3, c over a is c minus b, a minus b cubed. Therefore, c times a minus b cubed is a times c minus b cubed. This is a rather hard problem, but what you have to realize that the roots satisfy the original equation, right? The quadratic equation. And the key here was that when you put x2 in the quadratic equation, you end up with x2 squared term, which is the other root, x1. So this also gives another relation between x1 and x2. And then we use this fact to go and simplify and prove the problem. Okay? 5. If the ratio of the roots of equation ax squared plus bx plus b is 0, remember this, the last term is not c, it's b. Ax squared plus bx plus b equals 0 is p over q. So we have two roots, x1 and x2, and let's assume that x1 over x2 is p over q. Right? This is the ratio of the roots. And our quadratic equation is ax squared plus bx plus b is equal to 0. Okay? Then it says that prove this relation between pq and qp equals square. So what is basically what we need to prove is square root of x1 over x2 plus square root of x2 over x1 is the square root of b over a, right? But this is a symmetric expression. If I want to find the value of over x2 plus x2 over x1, which is p over q plus square root of q over 1, q over p, I square it, it becomes x1 over x2 plus x2 over x1 plus twice the multiplication, which is 1, right? But then again, this is a symmetric expression, becomes x1 squared plus x2 squared over x1 x2 when I make a common denominator plus 2. Therefore, a squared is s2 minus 2p divided by p plus 2, and it's s2 over p. Very simply, it's very nice. And remember, a is positive, so a is s over square root of p. Very nice. So what is s? x1 plus x2 is minus b over a. Let's put that s in absolute value. And what is p? x1 x2 is c over a, but c is b, so b over a, right? So s is minus p, and therefore a is p divided by square root of p. So this is square root of p squared divided by square root of p. Obviously, we're assuming that p is positive. It's square root of p, square root of b over a. So this is a rather easy problem. This wasn't really that hard. So a, our original x1 over x2 plus x2 over x1 squared, is square root of b over a. Done. All right. The next one, if p and q are roots of x squared plus rx plus s equals 0. So this is a quadratic equation in the standard form. Quadratic equation in the standard form, right? Remember, the standard form was such that the coefficient of the leading term, x squared, was plus 1. And r and s are roots of x squared plus px plus q equals 0. What is the sum? This is a very interesting question, very interesting question, right? Basically what happens here is that it says p and q are roots to x squared plus rx plus s, and then r and s are roots to x squared plus px plus q equals 0. It's very interesting, right? And then the question asks, what is p plus q plus r plus s? What is this? All right, how do we solve this? What do we know? From the sum and products, we know that p plus q is minus r, pq is s, and we also know that r plus s is minus p, and rs is q, right? So so from here we conclude that p plus q plus r should be 0, and let's call this parameter that we're looking for the sum of p, q, r, s capital A. Okay, and from the second one we realize that r plus s plus p, right? And what does this tell us? And so if p plus q plus r is 0, so it's equal to r plus s plus p, right? So p cancels out, r cancels out, q should be equal to s. Otherwise these two terms cannot be 0 simultaneously, okay? If q and the other thing is that if p plus q plus r is 0, then a, let me write it down. Basically a should be equal to s. Here a equal to q, right? And therefore because a is the same, so q and s should be the same. So that's the first conclusion that we're making here. Q and s are the same, and that's actually the value of the sum that we're looking for. And then if q and s is the same, pq equals s, therefore pq equals q. Therefore q times p minus 1 is 0. So we have either q is equal to 0 or p is equal to 1. Now if q equals to 0, then s is equal to 0, and regardless of p and r, we end up with the sum is equal to 0. Okay, now the other case is if q is not 0, therefore s is not 0, because q and s are equal, therefore p is 1, right, because of this term. And if p is 1 and r the other equation is this one, right? And the same thing, q times r minus 1 is equal to 0, and r should be 1, 2, right? And if this happens, then we know that p plus q should be negative r. So 1 plus q is negative 1, q is negative 2, or s is negative 2, right? Therefore a is equal to q is equal to s is negative 4. So a is either 0, which happens when q and s are 0, And if Q and S are 0, then P and R are have opposite signs, are negative of each other. P is minus R. So we have two sets of solutions, two sets of possibilities, let's say. Q equals S equals 0, and P is negative R. Um, P is negative R. In this case, S is A is 0, the sum of the four parameters, or Q equals S is not 0, or basically let's say negative 2, and P is equal R equal 1, therefore A is negative 2. Okay? Alright, problem 7. If x1 and x2 are roots of ax squared plus bx plus c equals 0. So x1 and x2 are the roots of this standard quadratic form, right? Again, this is a quadratic form which we studied in details, all the aspects of it. Prove this relation. Okay, this is also an interesting relation. And these are the roots, right? So when we get this, the things that we immediately know is the sum of the two roots, which is minus b over a, and the product x1 x2 c over a. And when we look at the left hand side here, left hand side, we see that it's a symmetric expression, which means that if I interchange the position of x1 and x2, it gives me the same thing. But before starting to simplify, just by looking at the expressions ax1 plus b and ax2 plus b that appear in the left hand side, this reminds me of ax plus b, right? Where do I see this ax plus b? In the ax squared plus bx plus c equals 0, right? Look at this. If I factor out x, I end up with ax plus b, right? Plus c equals 0. So, in fact, ax plus b should be minus c over x. Very, very clever trick. Very clever trick. Here. And since x1 and x2 are roots, now obviously we expect that they satisfy the quadratic equation, which means they satisfy this equation. So ax1 plus b is actually minus c over x1. Therefore 1 over ax1 plus b is minus x1 over c. Okay, same thing, ax2 plus b is minus c over x2. Therefore 1 over ax2 plus b is minus x2 over c. And if I square this, 1 over ax1 plus b squared is x1 squared over c squared. The same thing for x2, ax2 plus b squared is x2 squared over c squared. And therefore our left hand side is equal to the sum of the two, x1 squared over c squared plus x2 squared over c squared, 1 over c squared x1 squared plus x2 squared, which is 1 over c squared s2 minus 2p, 1 over which is equal to 1 over c squared b squared over a squared minus 2p, 2c over a. Make a common denominator of a squared, bring it out, it's 1 over a b squared minus 2ac. And that's exactly what we are looking to prove, right? So the clever trick here was that instead of trying to mindlessly simplify ax plus b squared on the left hand side, we realized that we can write it in another form. If we understand that x1 and x2 satisfy the original quadratic equation. So ax plus b should be minus c over x. And therefore 1 over ax plus b is minus x over c for both x1 and x2, right? And that helped us a lot because it's very easy to write x1 squared plus x2 squared in terms of s and p, which is s squared minus 2p. Alright, problem 8. If x1 and x2 are roots of x squared minus a plus d x plus ad minus bc, this is a quadratic equation in the standard form, right? Again, as a reminder, standard form is the form that the leading term x squared has a coefficient of plus 1. Then prove that x1 cubed and x2 cubed are roots of this quadratic, which is a little bit scary, equation. Y squared minus some coefficient times y, let's call it capital A, and some coefficient, let's call it capital B, and it's also in the standard form, right? Alright, how do we prove this? Remember, we had two methods. The method 1, or the direct method, was to define a mapping between the roots. Define mapping. Mapping here is x cubed is y, because we're looking for a quadratic equation whose roots are the cubed of the original one. And then inverse that mapping, x1 y over 3, and then put it in the original quadratic equation, y 2/3 minus a plus d y 1/3 plus ad minus bc equals 0. But then the problem is that this is not a polynomial, right? Not a polynomial, because the power of y is not an integer number, right? But what can we do here? We can we know that if we take this term and raise it to the third power, we get y squared. Similarly here, if we take y to the 1/3 and raise it to the third power, we get y. More importantly, we know that if we multiply these two terms, right, y to the 2/3 times y to the 1/3 is y to the 3 over 3 is y. It's also a polynomial. So let's do this. Let's bring the AD minus BC to the other side. Y 2/3 minus A plus D y 1/3 is minus AD minus BC. And raise everything to the third power. Raise to the third power. What happens? We know that x plus capital Y third is x cubed plus y cubed. Okay? I mean, I'm going to use u and v to not get confused with the small. So u and v to the third power is u cubed plus v cubed plus 3uv u plus v, right? Okay? Now, let's assume that our u is y to the 2/3 and v is minus a plus d y to the 1/3, okay? Now the thing is that we already know what u plus v is, right? U plus v is minus ad minus bc. So if I raise the whole thing to the third power, I end up with minus ad to the third power. This is the right hand side of that equation, and the left hand side is u cubed y2 plus v cubed minus a plus d cubed y. Okay, this is great. plus 3uv, 3u times v. But what is u times v? U times v is minus a plus dy. And that's very important to realize. Now we're getting a polynomial with the integer power. So minus 3uv, minus 3u times v, a plus dy, times u plus v. But what was u plus v? It was minus ad minus bc, right? So what do we end up with? We end up with y squared minus or plus y times some coefficients minus a plus d cubed plus 3 a plus d ad minus bc y plus ad minus bc cubed is equal to 0. Okay, now it seems quite similar to the original one. Ad minus b cubed here, 1 here. We have to just simplify this coefficient. Okay, and we called it so we already calculated this b. We showed that it's exactly the same. What is this a? Let's factor out the minus sign and a plus d here, or yeah, we can or we can just factor minus negative here, a cubed plus d cubed plus 3a squared d plus 3a d cubed a d squared minus 3a squared d plus 3abc minus 3a d squared plus 3bcd, and 3a d squared cancels out, 3a squared d cancels out, and a becomes minus a cubed plus d cubed plus 3abc plus 3bcd. And that's indeed correct. Minus a cubed plus d cubed plus 3abc plus 3bcd. So in this case we used the first method and did a direct mapping, but we didn't end up with a polynomial right out of the bat. So we had to do some manipulation of the equation, and we use the fact that y to the 2/3 times y to the 1/3 gives me a polynomial y. We use that, we raised both sides to the third power, and then we were able to take a polynomial out of the equation eventually. Okay, all right, next problem. Alpha and beta are roots of x squared plus ax plus b equals 0. So we have a quadratic equation which is in the standard form because the coefficient of the leading term x squared is plus 1. So alpha and beta are the roots of this one, and beta and gamma are the roots of x squared plus cx plus d. So these two equations have one root in common, which is beta. Okay, suppose 2 over beta is 1 over alpha plus 1 over gamma, and this is also given. Prove that 2a minus c squared is b minus d, b over d minus d over b. Okay, alright, so x squared plus ax plus b is 0. The roots are alpha and beta. X squared plus cx plus d equals 0. The roots are beta and gamma. So beta is common root, right? And if you recall about the common root, we know that beta satisfies the two equations. So beta squared plus a beta plus b is 0. Beta squared plus c beta plus d should be equal to 0. And if we subtract these two from each other, we end up with basically a minus c beta plus b minus d should be equal to 0. Beta should be minus b minus d, a minus c. Okay, so we're getting somewhere. We were able to take out some a minus c and b minus d. All right, but the other thing is that um, uh, we already expected that. Remember, in the general case, if we had two quadratic equations, right, that had a common root, had one common root, just one common root, or one root in common, and we called it t, and t was s minus s, or p minus p prime, s minus s prime. Difference of the product, delta p delta s, or maybe let's not use delta so that it's not confusing. And obviously we can this common root here is beta, p is b, p prime is d, s is minus a, and s prime is minus c. So minus b minus c, right? So let's write it down. Alpha plus beta is s, which is minus a. Alpha beta is p, which is b. Beta plus gamma is s prime, which is minus c. And beta times gamma is beta times gamma is p prime, which is d. Okay, now what do we infer from 2 over beta is 1 over alpha plus 1 over gamma? Well, 2 over beta is 1 over beta plus 1 over beta. The fact that I'm putting this in this format is because I want to bring the alpha and beta together and beta and gamma together, and then use the s and p's to simplify the thing. So 1 over alpha 1 minus 1 over beta is equal to 1 over beta minus 1 over gamma, right? And then basically alpha beta minus alpha is equal to beta gamma and gamma minus beta, right? Okay, the other thing was that if I have a equation x squared plus ax plus b equal to 0, right? X1 minus x2, if I square it, it's x1 squared plus x2 squared minus 2x1 x2, so it's basically s squared minus 4p, right? So x1 minus x2 is square root of s squared minus 4p. Okay, so for the first quadratic equation I have the difference of the two roots and the product. For the second one, the same thing, and let's just square it. So beta minus alpha over alpha beta squared is gamma minus beta over beta gamma squared, right? And beta minus alpha squared is from the first equation, is s squared minus 4p divided by p squared is equal to s prime squared minus 4p prime divided by p prime squared. All right, let's see what we're having here. S squared now what we need to get at is we have to bring out a minus c, b minus d, all right, let's see what happens here. S, what is s is minus a, so a squared. What is p is b, minus 4b divided by b squared should be equal to c squared minus 4d divided by p prime d squared. So this is our relation. Somehow we have to, so basically we have to factor b and d together, a and c together, right? That's how the original thing is given. A and c on one side, b and d on the other side. Okay, let's see how we can do that. Let's see. A squared 2a minus c squared. Let's call this common ratio something like k, okay? So k is a squared minus 4b divided by b squared, which is equal to c squared minus 4d divided by d squared. Okay? And what this gives us is that a squared is basically k b squared plus 4b, and c squared is k d squared kd squared plus 4d, right? So a minus c, I'm subtracting the sides, right, is equal to k b squared minus d b minus d b plus d plus 4b minus d. So I can factor out b minus d, and I end up with k plus, okay, let's see, I end up with b minus d times k b plus d plus 4, right? Okay, let's see. Two a minus c squared, a squared, a minus c squared. uh, let's see. Let's start with the right hand side, and or maybe left hand side. So in the left hand side, we have 2a minus c squared, which is 2a squared plus c squared plus 2ac, right? And if I want to see how to simplify this, um, b minus d, let's see, b plus d, and the right hand side is b minus d times b over d minus d over b, right? Okay, so we ended up with this relation between A, B, and C and D. But then the question is, how do we convert this from that to the original one? Well, let's have a look at what is the original expression. 2a minus c squared is b minus d times b squared minus d squared, which is b minus d, b plus d, right? But this is basically b minus d squared b plus d over bd, right? And I can also write this in terms of b minus d squared 1 over b plus 1 over d. But then this is 2a minus c over b minus d squared is 1 over b plus 1 over d, right? So we have to prove this. And we know that 2 over beta is 1 over alpha plus 1 over gamma, right? And the other thing is that we already established that beta is p minus bp prime, p minus p prime divided by s minus s prime, and we actually calculated beta. This common root was minus b minus d over a minus c, and therefore, very interestingly, a minus c over b minus d squared is 1 over beta squared, right? So what we need to actually prove is that 2 over beta squared is 1 over b plus 1 over d. And this is very simple, right? Because I take the original one, 2 over beta equals 1 over alpha plus 1 over gamma, multiplied by 1 over beta. 2 over beta squared is 1 over alpha beta plus 1 over alpha gamma, which is 1 over p plus 1 over p prime. Remember what p was? P was b and p prime was d. 1 over v plus 1 over d. So done. So we start with the expression that is given, multiplied by 1 over beta. We realize that 2 over beta squared is 1 over b plus 1 over d. But then we know that if we have two quadratic equations that have a common root, the common root is p minus p prime over s minus s prime. So 2 s minus s prime p minus p prime squared is 1 over b plus 1 over d. And therefore 2 s was a and s prime is minus c, so a minus c b minus d squared is 1 over b plus 1 over d. And if we simplify, 2 minus a c squared is b minus d squared 1 over b plus 1 over d, okay, which is b minus d times b over d minus d over b. So this is done. And that was actually a very interesting problem. Alright, this concludes our discussion on the quadratic equation. Next, we look at the more general case of polynomials and their properties. Thank you for paying attention.